Hello everyone, I am Natan Bulgarelli. I'm a postdoc at Research Line 2 related to production optimization at Epic, and I will present to you the emulsions flow rating within the ESP from experimental approach to the oilfield application. This topic is related to my PhD project and my temporary research work at Equinor. And to present this topic, I'll divide my presentation in 5 sections here, which we have in the first one and the second one, the outstanding investigations about emulsions as a flow assurance problem within the ESP, and the second one, outstanding results about the validation of our models in a laboratory environment. Both sections is related to my PhD project. And the third one is related to validation of our models in a relevant environment, which is related to my initial activity at my temporary research work. And the last 2 sections is related to development of the flow rate estimation to estimate the emulsions flow rate within the ESP. So the first step is to try to understand what happens when we have these 2 immiscible fluids here, water and crude oil, passing through a ESP, and due to its turbulence and shear, we can form the water and crude oil emulsions inside of this equipment, depends on the water fraction, and then there is a particular behavior when we have this kind of flow pattern within the ESP, and this behavior is related to the effective viscosity of emulsion. So we can observe here the relative viscosity in function of the water cut. So we can observe an increase of this parameter when we increase the water cut. So we have an intense increasing of this emulsion viscosity, and to illustrate this impact on the ESP performance, I'm using these performance curves here related to the ESP. And in the continuous line, you have ESP operating with water, and the dashed line related to the viscous fluid passing through the ESP. So you can observe that we have a reducing the ESP performance, and now we would like to understand and then to predict this ESP performance for different emulsion systems. So for this, the first step was to perform an experimental investigation using these 3 different emulsion systems here, and after that we observed different behaviors within the ESP, and then we propose a criterion to separate the different relative viscosity behavior within the ESP, and after that we propose a viscosity model to predict the relative viscosity for water and oil stable emulsions within the ESP. So the first step, we need to understand and analyze one of these performance curves of ESP, and here we have an important parameter, so the relative dimensionless head in function of the water cut, and you can observe an intense degradation of this parameter when we have stable emulsion systems, and then we have an opposite behavior when we have a stable one. And then now we would like to understand why this behavior is happening, and then we estimate indirectly the relative viscosity within the ESP. So here we have the relative viscosity in function of the water cut for these 3 emulsion systems tested. So, and you can observe that we have an increase of the relative viscosity when we increase the water cut for stable emulsion systems, and again the opposite behavior when we have a stable one. Thus, to separate these different behaviors related to the relative viscosity within the ESP, we propose this criterion here, the slip relevance criterion, which is based on this initial hypothesis, so a slip between the droplet, the water droplet, and the continuous phase within the impeller. And then we adopted some theoretical basis and proposed the boundary to separate these two different behaviors that we observed based on this new dimensionless number, the sleep relevance number, and this new model for Salter mean diameter for the ESP conditions. And then applying these both equations, we propose this criterion here. And to exemplify this criterion, I'm using this graphic here, so the relative viscosity in function of this sleep relevance number. And we can observe here two different regions separated by this critical sleep relevance number obtained from the experimental data. And in the first part, we have an increment of the relative viscosity, and then we associate this behavior to the homogeneous behavior. And the second one, we related this decrease of the relative viscosity for the sleep behavior. So after that, we propose the relative viscosity model for water in oil with stable emulsion passing through ESP. This model was based on the Taylor's model and some important dimensionless numbers observed from experimental results and visualization experiments. And then we applied this model on the Biazussi model to obtain the dimensionless head, and then we perform a comparison between our model and the lab test data, and then we observe a good agreement in both cases for stable emulsion and stable emulsion with the emulsifier. In order to investigate the relative viscosity behavior within the ESP regarding of the ESP operational parameters, we perform this sensitive analysis here, which we have the relative viscosity in function of the dimensionless flow rate for different water cut, and you can observe here a decrease of the relative viscosity when we increase the dimensionless flow rate for this mixed ESP model tested. So recently, the master's degree student Andrei Pulido performed some experimental tests, and he observed this behavior here. So here again we have the relative viscosity in function of the dimensionless flow rate for the same water cuts, but we have here a different stable emulsion system, but we can observe the same trend that you observe in our sensitive analysis. So after that, it starts my activity related to validation in a relevant environment of our model for our relative viscosity model. So the first step was to select ESP oilfield data, lab data, and well test data, and pass this data from data selection and pre-processing. So after that, we selected this data, and then we select the ESP that we have for each well, and then we need to calibrate the ESP dimensional set for each well and ESP. So for that, we use the lab data provided by vendors and some ESP geometric characteristics. After that, the third part was to calibrate the FT viscosity using the well test data and the fluid properties at ESP conditions. And finally, initial validation using oilfield data. So we need to perform this cycle process for each well and each ESP, and then we have effective viscosity model for each case. So the first part was related to the data selection and pre-processing. In this case, we analyzed the well test data for 38 wells. So we passed all these well tests to these criterions here, and after that we were able to use only these two wells, the well A and B, and we have here the viscosity and density in function of the temperature for each well. And after that, from this well selection, we can select the ESP model. So we select this model, and we took the viscous lab test for this these ESP models, and we separate half of this data for training, and another half to test. And here we have the comparison between the dimensionless head predicted and dimensionless head measured for both wells and ESPs, and we can observe a good agreement for this both case. After that, the third part is to calibrate the effective viscosity. So we use in this case the well test data. So we adopt the same strategy here. So we have half of the data for train and another half to test our model. And here we have the test data. So we have the dimensionless head measured and dimensionless head predicted for using our relative viscosity model on the Biazussi's equation for both wells and both ESPs. And we have a good agreement in this comparison as well. And finally, we started the initial validation. In this case, we compare the ESP lift capacity for water in oil emulsions without emulsion breaker. So we perform this comparison here. So we have the differential pressure predicted and differential pressure measured for the both cases, and we can observe a good agreement in both cases, but we have a little deviation because of some uncertainties that we have at the fluid properties and the total flow rate. And finally, during my temporary research work at Equinor, we propose a new flow rate estimation tool. So we do like to provide an additional method to estimate the emulsion production flow rate beyond the PAC. PAC is an official flow rate estimation tool developed by Equinor and Baker Hughes. And this method, we need to calibrate the effective viscosity for each increment of water cut, but when we use our model, we have a continuous estimation of this relative viscosity within the ESP. And for PAC, we need to solve many equations to obtain the total flow rate, but here we need to solve only these equations here, and a quite simple numerical methods is enough to calculate the total flow rate. And we perform a comparison between the total flow rate estimated by the new model and the total flow rate estimated by PAC for these both wells here. So we can observe a huge deviation in both cases, but especially here at the low total flow rates in both cases. After this analysis, we start to implement this new methodology in a workflow at the IVM software. And now I finalize my presentation, and I would like to thank all of these sponsors here for supporting me during my PhD project and now at my postdoc activities. Thank you very much for your attention, and I hope to see you at conference and answer your questions. Thank you very much.